Right now, you weigh exactly what you weigh. Tomorrow morning, imagine you woke up and you weighed twice as much without gaining a single pound. Your bed would feel different under you, your legs would feel different under you. And you wouldn't understand why until you looked outside and realized the whole planet had changed size overnight. This is the thought experiment. What if Earth suddenly became twice as large? Not twice as far from the sun, not twice as old, just twice the size, twice the width, twice the mass, still spinning, still orbiting, still yours. It sounds simple, it isn't. Doubling a planet doesn't just make everything bigger, it rewrites the rules underneath everything you've ever taken for granted. So let's start with the part your body would feel first. When scientists talk about doubling Earth's size, they usually mean doubling its radius, not just scaling up a photograph. And that distinction matters enormously because volume doesn't grow the same way width does. If you double the radius of a sphere, you don't double its volume. You multiply it by 8, double the radius of Earth, keep the same rocky density throughout, and you're not looking at a slightly bigger Earth. You're looking at a planet with roughly 8 times the mass. That single fact changes everything else that follows. More mass packed into a larger sphere means more gravity pulling down on every object at the surface, including you. The math isn't perfectly one-tune because gravity depends on both mass and the distance from the center, and a bigger planet pushes you farther from that center too. But run the numbers with a rocky planet twice Earth's radius and roughly 8 times its mass, and you land somewhere around double Earth's surface gravity. Maybe a bit more. Maybe a bit less depending on how the interior is structured. Either way, you would feel heavy, not slightly heavy, profoundly heavy. What would that actually feel like? Cardiovascular researcher Alan Hargens has spent decades studying how gravity affects the human body, largely through NASA-funded research on astronauts and long-term bed rest studies. His work shows just how sensitive your circulatory system is to gravitational load. Your heart already works constantly to push blood upward against Earth's regular gravity, especially into your brain. Double that gravitational pull, and your heart suddenly has to work far harder just to keep blood moving normally. Standing up too quickly might make you dizzy. Long periods on your feet could become exhausting in ways they never were before. Your bones and muscles, which already exist specifically to fight gravity's constant downward pull, would face a load they were never built for. And it wouldn't just be uncomfortable. Over time, it would reshape you. There's a reason large land animals on Earth already look the way they do. Elephants have thick, straight legs built almost like structural pillars, nothing like the springy legs of a mouse. This isn't a coincidence, it's physics, the biologist J.B.S. Haldane explored this idea almost a century ago in his classic writings on scale and size, pointing out that as animals get bigger, their weight increases much faster than the strength of their bones and muscles can keep up with. Weight scales with volume. Strength scales with cross-sectional area. Those two numbers grow at completely different rates. So what happens when gravity itself doubles on top of that existing imbalance? Every land animal on Earth would face a kind of double penalty. Not only would gravity be pulling twice as hard, but the animals themselves would still be built at their current sizes, with skeletons calibrated for the old rules. Tall creatures would struggle the most. Think about giraffes or humans standing upright for that matter. Structures that are tall and narrow are the first to become mechanically unstable when the load pulling down on them increases. Over evolutionary time, you'd expect life on a heavier Earth to trend shorter, squatter, and wider. Not because anything chose that shape. Because anything built differently would eventually break. Would trees survive at all in a world like this? Not the way you know them. Height in trees is a constant battle against gravity, using rigid trunks to hold leaves up towards sunlight. Double the gravitational pull working against that trunk, and the tallest trees on Earth today, sequoias reaching hundreds of feet into the sky, would become structurally impossible. Forests on a doubled Earth would likely look shorter, denser, and more sprawling, spreading outward instead of upward, because upward would simply cost too much. But gravity is only the beginning of this story. The ground beneath your feet would be behaving strangely too. Here's where the science gets genuinely surprising and where a common assumption turns out to be wrong. Many people assume that a bigger, more massive rocky planet would automatically have more geological activity, more heat, more volcanoes, more shifting continents. It seems intuitive. Bigger planet, more energy, more motion. Geophysicist Jun Kornaga's research complicates that story significantly. Kornaga studies how plate tectonics actually work and how they might work differently on planets larger than Earth. His research suggests that increased mass doesn't necessarily mean increased tectonic activity. In fact, it can work the opposite way. Higher gravity presses down harder on a planet's rocky plates, potentially making them thicker, stronger, and more resistant to breaking apart and sliding against each other. Plate tectonics on Earth depends on plates being able to crack, bend, and slide beneath one another at boundaries. If gravity squeezes those plates into thicker, tougher slabs, that entire sliding, cracking process could slow down or even stop. So a bigger, heavier Earth might not be a more geologically violent world, it might be a strangely still one. Why would that matter so much? Plate tectonics isn't just about earthquakes and volcanoes, it's part of what keeps Earth's climate in long-term balance. Volcanic activity releases carbon dioxide from deep underground, while weathering rock at the surface pulls carbon back out of the atmosphere. This slow tug-of-war has helped stabilize Earth's temperature over hundreds of millions of years. If plate tectonics slowed dramatically on a bigger, heavier Earth, that natural thermostat could break down. Carbon dioxide might build up in the atmosphere with nothing to reliably pull it back out. Over long stretches of time, that could push the whole planet toward a hotter, less stable climate, not because the sun changed, but because the ground itself stopped doing its job. What would be happening deep inside this bigger planet, far below anything you could see? Planetary scientist Diana Valencia has built detailed models of the interiors of super-Earths, rocky planets larger than our own, studying how their cores, mantles, and crusts might differ from Earth's familiar structure. Her research suggests that on a much more massive rocky planet, pressure deep inside increases dramatically. Rock and metal that would flow relatively easily inside Earth's mantle could become far more rigid and compressed under this new, heavier version of Earth. That matters because Earth's mantle constantly churns in slow motion, carrying heat upward from the core, and that churning helps generate Earth's magnetic field. Could a bigger Earth still protect itself the way it does now? That's an open question, but it's not a comfortable one. Earth's magnetic field comes from swirling liquid iron deep in its outer core, a process scientists call the geodynamo. That field acts like an invisible shield, deflecting charged particles from the sun that would otherwise strip away the atmosphere and bombard the surface with radiation. If the internal structure of a much more massive Earth behaved differently, if convection slowed down or the core solidified in unexpected ways, that shield could weaken. And a weaker magnetic field doesn't just mean prettier auroras. It means a planet more exposed to solar radiation and potentially more vulnerable to gradually losing its atmosphere into space over long timescales. Which brings up an interesting twist, because in the short term at least, this bigger Earth's atmosphere might actually behave in the opposite way. Stronger surface gravity is very good at holding onto gases. That's part of why small, low-gravity worlds like Mars have thin atmospheres that leaked away over billions of years, while Earth, with its steadier gravitational pull, has held onto a thick, breathable one. Astrophysicist Dimitar Sasolov, whose research on super-Earth's and habitability has helped shape how scientists think about planets larger than our own, has pointed out that bigger rocky planets are often expected to retain thicker atmospheres than Earth's, precisely because of this stronger gravitational grip. So which is it? Would this bigger Earth choke on a thick, heavy atmosphere or lose everything to a weakening magnetic field? Realistically, it depends on timescales and on details we can only estimate rather than know for certain. In the near term, more gravity almost certainly means more atmosphere, likely a denser blanket of air pressing down at the surface. Breathing itself might feel different, thicker, heavier in your lungs with every inhale. Over the long term, if the planet's magnetic field weakened due to changes deep inside, that thick atmosphere could slowly erode away, particle by particle, over millions or billions of years. This bigger Earth might start out smothered in air and end its story stripped and exposed, depending entirely on what's happening in a core you'd never see. And what about the oceans, sitting on top of all of this? Water behaves according to gravity too. A stronger gravitational pull compresses everything closer to the surface, including oceans. On this doubled Earth, with mountains structurally forced to be shorter and squatter thanks to gravity's unforgiving math, ocean basins might end up relatively shallower compared to the height of the land around them. Waves would behave differently, moving with more force per unit height, because gravity itself sets the rhythm of every wave that rolls across open water. Storm surges, currents, and tides would all be recalibrated by an invisible hand pulling twice as hard. Would a day on this planet even last as long as it does now? Doubling a planet's size and mass doesn't automatically change its rotation speed. But if this new Earth formed with different internal dynamics, or if its moon, if it even kept the same moon, interacted differently with a more massive planet, day length could shift too. A tidal relationship that took billions of years to slow Earth's spin down to 24 hours might play out completely differently around a planet this much heavier. You might end up with a longer day, or a shorter one, shaped by a tug-of-war between the moon and a planet that no longer resembles the one that raised it. Step back for a moment. What would all of this actually look like from a distance from space? Picture a version of Earth that looks familiar at first glance: blue oceans, green and brown continents, swirling white clouds, but look closer and something feels wrong. The mountains don't rise as sharply. The atmosphere looks thicker, hazier, pressing closer to the surface like a heavier blanket. Below, forests spread wide and low instead of reaching upward. Somewhere in there, creatures with thick, stocky legs move slowly across flat plains, built by generations of gravity ruthlessly editing out anything too tall, too thin, too delicate to survive. And somewhere in that world, if humans existed at all, they wouldn't look quite like you. Shorter, sturdier, built low to the ground, the same way every successful animal on that world would be, because gravity doesn't negotiate and it doesn't make exceptions. Here's the part that's easy to miss in all of this. None of these changes come from some dramatic, violent event. No collision, no explosion, no sudden catastrophe, just one number changing, the radius of a sphere doubling quietly overnight. And from that one simple change, an entire cascade follows. Heavier gravity reshapes bodies. Reshaped bodies limit what life can become. Compressed plates slow the shifting of continents. Slower continents disrupt the planet's long-term climate balance. Changes deep in the core ripple outward into the strength of the magnetic field. The magnetic field decides how much atmosphere survives and for how long. Every piece connects to the next, like a chain reaction hidden inside a single act of doubling. Why does that matter to you, sitting here on the actual Earth, the one that never doubled? Because it reveals something you don't usually notice. Earth's exact size isn't just some neutral background detail of your existence. It's a precise, narrow setting that every living thing around you has been quietly built around. Your bones are exactly as thick as they need to be and no thicker. Trees grow exactly as tall as gravity allows and no taller. Plate tectonics moves at exactly the pace needed to keep carbon dioxide in balance, keeping the climate livable across hundreds of millions of years. None of this was designed. It simply survived generation after generation, inside the very specific gravitational conditions of a planet this size and not one size larger. Change that one number and everything downstream has to renegotiate itself from scratch. Muscles renegotiate, skeletons renegotiate, mountains renegotiate, even the air renegotiates what it's willing to hold onto and for how long. So the next time you feel your own weight, standing up from a chair, climbing a flight of stairs, carrying something heavy across a room, remember what you're actually feeling. You're not just feeling your own body. You're feeling the size of the entire planet beneath you, quietly deciding in every single moment exactly how heavy you're allowed to be. Right now, you weigh exactly what you weigh. And somewhere underneath that ordinary fact is the entire hidden architecture of a planet that never doubled, holding you up exactly as much as it needs to and not one bit more.